I'll let that run and then we can move on. So expectations for this workshop, just to clarify about what level we're expecting. So generally you should have prior coding experience, and previous algorithms or data structure knowledge is highly recommended because we'll be using a lot of terminology that we're kind of expecting you to know or be familiar with. So an example would be taking CS 180. And previous competitive programming experience is not necessary, but it definitely helps in following along. And even if you don't meet or if you don't have these prior experiences, you can always feel free to just try to follow along. It might be a little more difficult, but it's not impossible. And if you have any questions about whatever topic we're going over, just feel free to ask any of the officers. Okay. And as for meeting structure, so currently we're planning on talking about topics for about 1 to 1.5 hours. And then the remaining time will probably spend be working on the code force problem set. So every week there would be a code force problem set, and we'll go over it in a little more detail about what code forces is toward the end of this meeting. And depending on how things go, we may or may not shorten it to 1.5 hours, but we'll have to see. Okay, so to begin, we'll be going over just some brief review about what graphs are. So a graph is generally consisted of two things, edges and nodes. So we can call nodes, nodes are like points, and edges connect these points. So if you think about them like points on the graph, and then you draw lines between these points, then the lines we draw are edges, and then the points are nodes. So that's a quick summary about how or what nodes and edges are and what graphs are consisted of. And as for edges, they can have weights or values associated with them. So if they have weights, they're called weighted edges. And then in general, a graph with weighted edges is called a weighted graph. And so you might be wondering, what are weights? So a weight can be almost anything. It can be numbers, it can be floats, it can be even infinity, it can be a word. So it really can be almost anything depending on what you're using the graph for. And so that's what a graph is. And so after the definition of graphs, there's a few types of graphs, and we'll mainly be talking about an undirected and directed graph. So as you can see in the pictures, the undirected graph is just a regular graph with nodes and edges. So the edges don't have a direction, but on the other hand, a directed graph, the edges have a direction. So that's why it's called a directed graph, because all the edges are directed in some way, while the undirected graph, the edges don't have direction. And sometimes the directed graph edges are called a unidirectional edge. And for undirected, it's called a bidirectional because you can go in both directions. So after that, we'll be going over the first algorithm that we'll be talking about today, and that's Dijkstra's algorithm. So suppose for this algorithm, we have a weighted graph. So it can be either directed or undirected. And in the case of this problem, the weights we'll have on our edges are going to be numbers. And this algorithm solves the following problem. So assume we're given a start and end node, and we want to find the shortest path between these two nodes. And by shortest path, I mean the minimum sum of weighted edges along the path we travel. If we start at some node and we follow a series of edges to go from one node to another and to go from the start to the end. So in the case of this graph on the slide, if we start from node 0, then the shortest path from 0 to 2 will be a weight of 4, because we can go from 0 to 1 and 1 to 2. So that'll be 3 plus 1, and we'll get 4. And so before we get into the actual algorithm itself, a few definitions will help. So we can let the array distance I be the smallest sum, or in other words, the shortest path from the starting node to node I. So this will be very important because we'll be using this in our calculations, and the algorithm will return the whole array distance at the very end. And our second definition will be relaxing an edge. So this might be slightly confusing, but assume we have an edge going from node A to B. So again, this can be directed or undirected. And if it satisfies this condition, so if the distance, the shortest path or the shortest distance from the start node to node B is greater than the shortest path from the start node to A, and then plus the weight of that edge, then we want to update the shortest path or the shortest distance to B. So essentially what we're doing here is that we're updating the shortest path to node B. Assuming we go from the shortest path of the starting point to node A, and then we take that edge, AB, to reach node B. Because we know that if we take this path from node A, and then we go across the edge from A and B, it will be a shorter path. Okay, so now onto the actual algorithm. So Dijkstra's algorithm uses a greedy approach. And in case you're not familiar with what greedy approach means, it's basically saying you want to take at every step the next best available of something. So in this case, we'll be choosing the closest node to some visited node. And that would be the greedy approach because we're repeatedly just taking the closest node. And so at every step, we take the closest node to some visited node. And at the very beginning, we just start with the source node. And then we mark that node, that closest node, as visited. And then for all its neighbors, we try to relax them. So going back to the definition of relaxed, we want to update the shortest path to all its neighbors if we go from that closest node to all its neighbors. And then we repeat this. And so here it says the time complexity is O of m log n. And then I'll explain this in a second why this is true. But for now, this is the time complexity, and that's how you find the shortest path between the source node and the destination node. And those two will be given. Okay. So there are multiple ways to implement this algorithm. So for the first step, we want to find the closest node to a visited node. And the easiest way we can do this is to scan through every single node and then just find the closest one. So on the right side here, you can see the code for this naive approach. The outside for loop is just running the algorithm n times because every single path will have at most n nodes. And then the inside for loop here, that is going through every single node and then finding the closest one. So that is what the first for loop is doing. And then after that, the relaxing part is in the second for loop, where we check every single neighbor. And then for every single neighbor, we use the condition, the criteria for relaxing an edge, and then we try to relax that neighbor. And if we do, then we just update its distance, and then we repeat. Yeah, so again, remember, if you have any questions, just feel free to put it in chat, and then we'll try to answer it as soon as possible. Okay, so yeah, so as for recordings, it should be, I believe, maybe Nikhil has more information on this, but it should be on the ACM YouTube channel. Yeah, so that's where you can find these recordings. They'll always be recorded, and you can just go to YouTube and find it on there. Okay. Okay, so is this algorithm, wait, is this algorithm running Dijkstra from one source? Oh, on the previous slide? Yeah, so this code on the right side, this is running it from a single source. So if you look at the Dijkstra function, it has a parameter int s, and that s is the source node. So it'll only run from one source node. In case you want the distance between every pair of nodes, you're gonna have to run Dijkstra from starting from every single node.
Okay, so then why are we iterating through like all of the nodes from like 0 to n-1?
Right, so we want to do this because, let me see, in the previous slide, here we want to choose the closest node to some visited node. So that's essentially what that first for loop is doing, iterating through every single node from 0 to n-1, and then checking whether or not it's distance. So in this case, it's dist I, if that's the smallest. And if it's the smallest, then we know that's the closest to some visited node. Since we only relax nodes that are adjacent to a visited node. So that's how we know that if it has a distance, then it has to be or a valid node for the next step.
Okay, so the outer for loop, we never actually do anything with node I, that we just know we have to do this n times. But then the inner for loop finds the closest node to a currently visited node.
Right. Yeah, so the explanation for the outer loop, node I, is that every single path will have at most n nodes, because if it has more than n nodes, then it's going to have a cycle. Because it's kind of similar to the pigeonhole, where if you have more than n, or if you run the algorithm more than n times, and there's only n nodes, you're going to have a repeat, which means you have a cycle. And obviously, in your shortest path, you don't want cycles, because that wouldn't be optimal. And the catch is, if there's negative edges, which we'll get to after Dijkstra's, then it might be optimal to have cycles. But Dijkstra's in this case, it'll work without cycles. And this is assuming that all edges are positive. Yeah, so that's the catch with Dijkstra's. Okay, and now the better way, because there is a faster way to implement Dijkstra's without having to loop through every single node every single time, and that's to use a priority queue. So what a priority queue is, oh yeah, here in the code it uses a set, but essentially a priority queue will sort all the elements inside it in some type of order. So it can either be increasing or decreasing. That's really up to you to specify. But since here we want to find the closest node, we will push the distance and the node ID itself as a pair into the priority queue. And since the priority queue sorts the distances by increasing order, then you know that the first element in the priority queue will be the closest node. So that's essentially what this code is doing. It's taking the first element inside the set, which does a similar thing as a priority queue. It also sorts the pairs by distance. And we take the closest one, we take that edge, delete it from the priority queue, and then we iterate through all of its neighbors and try to relax all those neighbors. And this is a lot faster because we no longer have to iterate through every single node. We just have to take the top of the priority queue. And at every single step, if we've relaxed some node, we can just push that node into the queue, the priority queue, and it'll automatically sort the distances for you. And that's how we reach the m log n complexity, because every single time there are m edges. And so the log part comes from the priority queue because it takes log time to store this information. And for every single node, we'll be going through every single edge. So that results in m time. So that's the rough explanation for the time complexity. Yeah, so I guess we'll do a poll right now. Okay, it looks like most people are okay with this. So not too many people are confused. Yeah, and for the people who want, oh yeah. Yeah, for the people who haven't filled out the poll, please fill out the poll so we know whether or not we can move on or not. For the people who would like an explanation again, maybe you can ask your question in the chat and then we can individually address those. Okay, so we can move on then. So I mentioned before that Dijkstra's does not work with negative edges. And so the question here is, how do we change Dijkstra's so that if we have a graph with negative edges, we can still use some type of algorithm to find the shortest path between a start and end node? And this is where Bellman-Ford comes in. So the Bellman-Ford algorithm, it's very similar to Dijkstra's. But not only does it work with negative edges, but it's very handy in detecting whether or not there are negative cycles in the graph. So when I mean cycle, if we go back to one of these graphs, by cycle, I mean you can go from one node and follow some series of paths or some series of edges and nodes such that you will always go back to the node that you started from without visiting any other node twice. So that's what a cycle means. And the problem with negative cycles is that since they're negative, you can just repeatedly follow that cycle infinitely, and your distance will just infinitely get smaller. And so your algorithm will fail in this case because it would just repeatedly take this, it would just repeatedly try to minimize your distance. And that's not going to work properly. So the idea for Bellman-Ford is that we want to run the algorithm n times, so very similar to the naive Dijkstra. And every time we run the algorithm, we want to, for every node, try to relax all its neighbors. So it's not just relaxing the neighbors of a visited node. We're trying for every single node to relax all its neighbors. And we do this n times. And after that, after we run this algorithm n-1 times, we can try relaxing all the neighbors, all neighbors of all nodes again. And if something gets relaxed, there is a negative cycle. And I'll explain this, why this is the case. But first, I want to explain why exactly this algorithm works. So the idea is that every path in this graph must visit each node at most once. So very similarly to why the naive Dijkstra runs only n times. But here in this case, we can run it n-1 times because we can notice that once we start from the first node, we're actually just at most adding n-1 nodes to it. Since if there's n nodes, so we'll add at most n-1 nodes aside from the initial node. So that's what the code is doing here. The outside loop, the loop with I in it, runs n-1 times, and the inside loop is going through all m nodes. Or in this case, actually, they store as edges. But for every edge, we try to relax the nodes on each side of the edge. So that's essentially what we're doing. It's the same thing as trying to relax every single neighbor of every single node. And if we look at how this algorithm works, we're running the outside loop n times, and we're running the inside loop m times. So the total time complexity will be n times m, which is slower than Dijkstra's, but the advantage is that it will work for negative edges. And so going back to how the negative cycle detection works, if we run the algorithm one more time, so the nth time, and something gets relaxed, then there is a negative cycle. And this builds on the fact that every single path has to have, or after we run the algorithm n-1 times, the algorithm should be over. So every single shortest path should be calculated by this point. And so if we run it one more time and something gets relaxed, that means we can make some path shorter when we supposedly cannot anymore. So this means that there is a negative cycle. And so that's how the negative cycle detection works. It's very handy. And if you think about it, you can actually use this as a positive cycle detection. So it might not be that obvious right now why this would be very helpful, but sometimes in the case of a problem, like in the context of a problem, you might want some type of positive cycle detection. And you can always, in this case, negate all the edges, just multiply every edge by -1 and then run this algorithm, and it'll still work. Okay, yeah, so that's it for Bellman-Ford. And again, we'll run a poll just to see if people want to move on or not. Okay, that looks good. Yeah, so we can move on then. So the third algorithm we'll be talking about, I believe this is the last one for today, is Floyd-Warshall's. So this is also a shortest path algorithm, which calculates the shortest path between every single pair of nodes in a given graph. And it does this in the form, we can store the distance in a matrix, a 2D array called, in this case, D. So Dij equals the shortest path between nodes I and j. And from this property, Dij should equal Dji, because the distance between nodes I and j should be equal to the distance between nodes j and I. we can just go backwards along the path and get the same distance. So that's just some property of this matrix. And so how does this algorithm work? And the general idea here is we want to choose every single node as an intermediate node on the path between any other two nodes. So this might seem a little confusing at first, but maybe looking at the code will help a little bit. So looking at the code, we have 3 nested for loops, and the outside is k, and then we have I and j. So I and j here will be the nodes, the 2 nodes that we're trying to calculate the shortest path between, and then k will be our intermediate node. So what the algorithm is trying to do here is we're trying to update the shortest path between nodes I and j with the shortest path between I and k and j. So if the path going from I to k and k to j is shorter than the current shortest path between I and j, then we update the distance with dik plus dkj. And we do this for every single k. And after we run this algorithm, it will give the shortest path between every single I and j. Yeah, so another visual representation. Here we have a graph of of 6 nodes. And we can start with node 1. So k equals 1 in this case. And then for every single pair of nodes, we want to try to update the distance AB with distance of AB and the distance between A to 1 and 1 to B. And then we try the distance between A to 2 to the B, and then so on. And we repeat this for every single AB, and for every single AB, we repeat this for every single K, basically. So this algorithm, looking at the code, there are 3 nested for loops. So this is going to be n cubed. And n cubed often is very slow. So for most cases, the advantage of Floyd-Warshalls is that it's very short to code. So looking at the code, it's very simple. You just need to code or create a matrix, and then you have 3 for loops, and then you're done. But it is actually faster to run a Dijkstra's. So going back to Dijkstra's, we can run a Dijkstra's from every single node, and that will calculate the shortest path between every pair of nodes. And this is faster than n cubed. So if you look at the time complexity, it will end up being nm log n, which is faster than n cubed. Yeah, so I forgot to mention this, but before you run all of these algorithms, the default case, since we're trying to minimize every single distance, we want to set the distance array to infinity. So some arbitrarily big value that we know the edge weights will never reach, or the shortest path will never exceed that value. So then this means that every single path in the graph will always be less than this, and so our minimizing function will work. Yeah, so about the Dijkstra for the set implementation or the priority queue implementation. So here, yeah, so set erase does have a time complexity, but I'm not sure if I remember correctly, but removing the beginning should be O of 1. And even if this is not, if you use a priority queue, it will always be O of 1 just to pop the top. Yeah, so hopefully that answers your question based on the time complexity for the sets. So generally, sets will be slightly small or slower than priority queues. So it's always preferred to use a priority queue over a set in this case. Okay, and so for Floyd-Warshalls, the algorithm actually works with negative edges as well. So even if there's negative edges, the algorithm won't break. So initially, we set everything to infinity. So again, some arbitrarily big value. And infinity, in this case, will mean that edge ij does not exist. So in the very beginning, we will only have a distance if two nodes are connected by an edge. So this is way before we're running the three nested for loops. It's just the base case. So assuming we have an edge, let's say from 1 to 2 of weight 5, then d of 1, 2 will equal to 5. So in other words, we want to update the distance matrix with all the values of edges, just between the distance between every adjacent two adjacent nodes. And so in the original implementation of Floyd-Warshalls, we might have a problem if there's negative edges, because let's say we have the infinity value, and then we add a negative number. Then, of course, infinity plus some negative number will always be less than infinity. And since it's less than infinity, we will interpret that as a valid distance. And so this will give us some problems in our implementation, and we don't want that. Because infinity also represents no edge. So we technically don't want to add infinity with something else. But fortunately, we only need to change one line of code in our implementation, and that is adding this if condition here. So we only need to check if the distances I to k and k to j are both less than infinity. So in this case, that means both of them have valid paths, and so you can add them together, and we'll get a valid shortest path between I and j. Okay, yeah, so that should be it. I guess we'll have a poll again in case we want to go over Floyd-Warshalls again. Okay, looks like mostly everyone is okay with this explanation. So I guess, okay, here is the attendance code for today. So it's just Dijkstra. Make sure you spell that correctly. And then here's a feedback form. Be much appreciated. All feedback is welcome. And so that is it for the lecture. And so we actually have a Code Forces contest that runs for a week. And it would be very helpful if everyone were to try a problem or two on that problem set. Be good practice for Dijkstra's, especially since Dijkstra's is the most common shortest path algorithm that probably appears, while the other two, Floyd-Warshall's and Bellman-Ford, are less common.